Can you guys confirm that you can see the slide?
Yes.
Great. So I do want to remind you guys that we are doing this through MCAT 101, and make sure to email me or MCAT 101 if you have any questions. And if you aren't part of the mailing list, please just put your email in the chat and I will add you to those lists. So since we are covering kinematics and work, I do want to start by going over the units. There are base units that we've assigned arbitrary measures to over the time, and that's things like length, where we have meters and feet, mass, where we have kilograms, time with hours, seconds, current with amps, amount with moles, and temperature with Kelvin or Celsius or Fahrenheit. Now, these units can also be combined to create derived units that we can use in other measurements for kinematics, like force, power, and work. And so here are a couple of the measurements for these units, like force, work, and power, which are very important to kinematics. And I do want to remind you guys that these equations that are on the slides will be important for some of the questions and also during the MCAT. So it would be best to remember and memorize as many as you can. So I'm sure you've all heard of watts and power, I guess, from cars or from microwaves and bulbs, but it's also used in kinematics. So the quantities used in kinematics and work, yes, we will have these presentations and recordings uploaded, so you should be good on that. And if you want a specific email, just let me know at the end of the presentation. But yeah, so for kinematics, there are two types of quantities that are measured, and that's scalars, which have a magnitude, but not a specific direction. And that is like speed. On a speedometer, we don't have a specific direction, just how fast we're going, energy, pressure, mass, and distance. Now, the other type of quantity that's measured in kinematics are vectors, and these have both magnitude and direction. And this has to do with things like displacement, which has to do with distance and direction, velocity, which has again to do with speed and direction, acceleration, which is why we have words like acceleration and deceleration, and force, which is always assigned a particular direction with respect to an object. Now, vectors are very important in kinematics, and so there is a bit of math that we do with vectors. And visually, you can always add and subtract vectors by using the tip to tail method as seen here, where you can put the tip of one vector at the tail of another. And this works commutatively when you're adding. Or you can use the component method, which does involve a little bit more involved math based on the angles of each vector and the Pythagorean theorem. So if you can visually draw vectors out, then I would say use that way because it is simpler if you just need a direction and a relative magnitude. But otherwise, if you want to be precise, you're going to have to use the component method. Now, there is also vector multiplication, and that's going to be used when we measure things like torque and direction of work as well. So scalars create a new vector. So we can, when we multiply a magnitude by a vector, and dot products and cross products will give us either a magnitude in the terms of a dot product or another vector in when we're talking about a cross product. And when we look at the cross product of two vectors, we're going to have to use the right-hand rule to determine the resulting vector, where the way I've learned it, it's always point your index finger in the direction of the first vector and then curl your fingers. In the picture, it shows just your middle finger. But what you want to do is put the first and second vectors at right angles using your index and middle finger, and your thumb will always point in the direction of the resulting vector. So now that we've covered the basic units and vectors and how to put them together, I do have a couple of questions for you guys. So feel free to type the answers to these questions in the chat when you have them, or unmute yourself. So far I am seeing a lot of B's as in scalar, and that is correct. Temperature is a scalar quantity because there is no real direction associated with it. So a second question for you guys. And for this one, I did put the equation that you'll want to use, but it's definitely better to memorize these equations for the actual MCAT. So for this one, I am getting a couple of different answers from you guys. So I think it's probably best that we all work through it together. So with this question, the real equation we really need to use is the one below for cross product. And what I did was I gave you the components for one vector and the magnitude for the other. If you want to convert from the components of a vector to the magnitude of a vector, you're going to have to use Pythagorean theorem. But in this case, that's relatively straightforward because there is no y component. So that means the magnitude of the vector is completely along the x-axis, and the magnitude will be 5. So when you plug those numbers into the equation here, you get the magnitude of A as 5 units, the magnitude of vector B as 8 units, and you need to take the sine of 30 degrees. Now, if you've taken trig, you will know that the sine of 30 degrees is 1/2, and that's a really important property to remember. So if you multiply 8 times 5, which is 40, and you multiply that by 1/2, which is the sine of 30 degrees, you will get 20 units as the answer. So the answer here is C. Now, I do have one last question for you guys before you move on, and this one has to do with the right-hand rule as a hint.
Can I actually ask for clarification on question 2?
So for this question, I am getting a couple of C's and B's, and that's completely understandable because cross product has to do, you cannot use commutative property in that you have to go from using a specified vector first and another vector second. So in this case, it would be A cross B. And you'd have to put your index finger towards the right side of the screen to get to point them towards vector A, and then point your middle finger a little bit upward in the case of vector B. And if you do that, you'll notice that your thumb is pointing back at you. So the answer would be out of the screen. And if you have any questions, please type them in the chat. Someone said there's a question for the last problem. I'm not seeing any questions, but if there is, please retype it in chat and I will get to you as soon as I see it. But if there are no other questions, I'll wait a couple seconds and then move on. Okay. What the approach would be in situations where there is a y component. So in that case, you would have to use Pythagorean theorem to find the magnitude of vector A. But since we are doing this without a calculator, I made it easy and left out the y component of the vector. How did I get B? For this question, I'll try to walk through it again. So I'll go back a couple slides, actually, that might help. When we look at the right-hand rule, what you notice here is cross product specifies a vector first and a vector second, and that isn't the case for a dot product. So with cross product, I mentioned that we were going to do a cross product of vector A and vector B. So vector A goes first, which means in this case where I specify vector A as 0 degrees and 0 degrees pointing to the right side of the screen, that would mean you'd point your index finger towards the right side of the screen, and vector B being at 30 degrees, which would mean in terms of quadrants, it would be quadrant 1. So a little bit towards the top right of your screen. So if you point your middle finger towards the top right of your screen and your index finger towards the right side, then your thumb, which should represent the direction of the cross product, will be pointing back at you. And that's why the answer is out of the screen. Does that make sense? It's really hard to draw it on a 2D screen because cross products are 3D. Let's see if I can. For directions, you point your thumb upwards toward the arrow and follow. There are definitely different ways to do it. It just matters that you have a way that works for you as long as it's the right way, because you can always switch your fingers around as long as you have them specifying the direction of a vector. But it depends if you're left-handed, there's going to be a different rule, so on and so forth. I will try to annotate on this page, but I will warn you guys that I am not the best at drawing. So for this case, vector A would be like this. So you'd point your index finger towards your right. I specified the right side of the screen, but it's really just to your right. And then vector B would be more like, let me change the color so you can get a better understanding. But vector B would be like this. Yes, this is the same rule that you use to predict for magnetic field and current and so on. It's just you use different quantities. So the vectors would be like current and so on, instead of just two force vectors. Yeah, but yeah. So if you point your index finger to in the direction of the black arrow, and then you curl your middle finger upwards towards the direction of the red arrow, your thumb should point at you if you're using your right hand. Please let me know if I need to clarify further, and I can probably do that at the end. But for now, if there aren't, oh, sorry. The picture I provided is just as an example, because I didn't want to draw the picture out, because that would make it a lot easier in terms of just pointing your fingers in the direction of the arrow. But yeah, so from here, we are going to move to kinematics. So an important distinction in kinematics is the difference between displacement and distance. Oh, looks like we may have, oh, great, that's great. And the distinction between displacement and distance is that displacement has to do with your start point and your end point, and distance has to do with the path in which you actually traveled. So when you calculate displacement, you're going to use a period of time, and you're going to see where you are at the beginning and where you are at the end, and calculate a direct line from there, as you can see in the image. But for distance, more than just your start and the end point, it matters the path that you took. And this is very important when it comes to calculations of velocity and speed, which are extremely important in kinematics. So I just want to make sure you guys get this part 100%. Velocity has to do with displacement. And what velocity is a calculation of the total displacement over a certain period of time. Speed, on the other hand, is your total distance divided by a certain period of time, if that makes sense. What you're going to see is that speed is not necessarily the same as velocity, because velocity and displacement don't care about where you were in between. They just care about where you started and where you ended during the period of measurement. Please let me know if there are any questions about this part, because this is a very important part of kinematics. All right. So force. Force is measured in newtons, which is the same as you'll see, mass times acceleration in the equation here, where mass is defined as in kilograms and acceleration as the distance covered divided by time, which gives you velocity. And you divide velocity by time again to see the rate of change of your velocity is your acceleration. And force is a vector because it acts on a specific object or a specific point in a certain direction. A force that we come into contact with all the time, or is basically part of our lives, is gravity. And that's what gives us our weight. And here's the equation for gravitational force. Now, this equation isn't very widely used, but it would help to understand the concept behind it. because it does explain the force upon us and the Earth, and why the Earth doesn't move from our force. So what G is in this case is a gravitational constant, which is a number that is arbitrarily determined for gravity. And M1 and M2 are the masses of the different objects that are attracting or repelling each other. In this case, attracting because gravity. And R is the distance between the two objects. So what this tells you is as the mass of the one or both of the two objects is larger, the gravitational force becomes stronger. And as the radius or the distance between them also gets larger, the gravitational force decreases. Yes, there is a similar one for electrostatics. And I'm not covering electrostatics, which is why I didn't really mention it, but you'll notice that there are a lot of similarities. Yes, Coulomb's law, thank you. I didn't remember the name, but it's the exact same, but instead of mass, you have charge. And you have an electrical constant. I don't remember the exact name of the constant, but instead of gravitational constant, it has to do with the charge of an object. So mass itself is a scalar because there's no particular direction on which it's exerted. It's just a measure of the physical part of anything, like how many atoms or how much particles are or how many particles are in it. Center of mass and gravity is very important for projectile motion, and it'll help you understand how projectile motion works, and that if you've ever balanced a pencil on your finger, you'll notice that there is a certain point in which the pencil balances perfectly. Now that in free body diagrams is where you can pretend that all the weight is concentrated. And if you follow as that path as you toss an object, as this person is doing with a bat in the image, you will notice that the center of mass follows a perfectly parabolic path. And this center of mass or gravity can be measured by doing almost calculus, but you multiply the masses and their locations on the object and divide by the total mass of the object to find the exact location along the object. Next, we have acceleration. Acceleration is a vector, and because it can be both positive or negative. And like I said earlier, what it measures is velocity's rate of change. The actual units are meters, so distance divided by seconds squared. So you get meters divided by seconds is velocity, and velocity divided by seconds is velocity's rate of change for each second. Now, there is a difference to average and instantaneous acceleration. What you'll notice is that the instantaneous acceleration is always tangent to the velocity, and the average acceleration is just how much the velocity changes over a certain period of time, not at any given moment. Now we come to friction, which is also an important part of our lives. Oh, there's a question. Never mind. So friction is a non-conservative force, and I will explain conservative and non-conservative forces later, but friction exists between the object and the surface that it's in contact with. And a related force is the normal force, which is the contact, which is a force that exists when there's contact between an object and a surface or another object where the force is perpendicular to the contact plane. So let's say we're all sitting in chairs. The force that that our weight is exerting on the chair is countered by the normal force of the chair holding us up. Now, friction has is determined by the normal force and the coefficient of static and kinetic friction, which are determined by the materials that the object is resting on. Static friction exists when an object is in stationary contact with something else. So let's say, I guess, whatever you're watching this on and the surface that it's in contact with. It's determined by the normal force. And what it means is you can exert a force up to the point where it exceeds the static force, which is determined by the normal force multiplied by the coefficient of static friction, which is what you see in mu n here. And up to that point, the object will not move because the frictional force is greater than the force you're exerting on it. Once you break past the limit, which is, again, the normal force multiplied by the coefficient of static friction, you then get into kinetic friction, which is always smaller than the force of static friction. And you'll have noticed this. If you ever try to push something, it takes more energy to start it moving than it does to keep it moving. And kinetic friction has to do with sliding contact, not stationary contact. And it's also a value that's based on the material that the object is sitting on. And someone mentioned, shouldn't the normal force be pointing up? Yes, in this case, the normal force should be exerted from the surface, which looks somewhat like granite, onto the block. I guess it depends on your relative view. If you flip it upside down, it would make sense. I actually didn't look that closely at it to notice. In this case, actually, the normal force, it's the normal force on the block, which is actually gravity in this case, if you're looking at it this way. Because both, as we'll get to later, Newton's third law mentions how objects that are exerting forces on, will exert forces on each other equally. So the question is, if an object is moving at a constant velocity, is the velocity greater than the kinetic friction, or are they both equal for constant speed? I will get to this later when I talk about resistance. But yes, that is why we have things like terminal velocity, where in free fall objects can speed up to a certain point where the friction equals the acceleration, and then they move at a constant velocity. I hope that answers your question. Does friction not exist without contact? Yes, it has to have contact for friction to exist, but it doesn't have to be like a solid surface. Like air resistance is a type of friction or drag. Well, if the object to HK, if the object is moving at a constant velocity, that's because the force pushing them forward and the friction driving them backward are the exact same. Yeah. No worries. One second. If there are no other questions, I will move on to the next slide. So now we have Newton's first law. And this is really well exemplified by static and kinetic friction, while once you start it moving, it tends to continue moving. And what Newton's first law is that it just tells you that an object will prefer to stay in the state of motion that it is already in. So as we were discussing earlier, at a constant velocity, whether it is zero, whether that velocity is zero or not, if the force does not exist, the object will continue to stay at that velocity, again, whether it is non-zero or not. And this is considering that the mass is non-negligible. For the second law, what Newton said is that any force that is exerted is equivalent to the mass times the acceleration. So what that means is, in practice, if you are trying to, let's say, roll a cupboard, no, not a cupboard, but like a tool rack down a hill, you're gonna have to push it harder. But let's say you pull out some of the drawers, it's gonna be a lot easier to push faster because there is less mass. So you'll get greater acceleration with the same amount of force exerted. And you'll notice acceleration is always going to be in the same direction of the net force. And it's always proportional to the net force because the mass is the only other thing that affects it. Thank you. And in the same way, acceleration is inversely proportional to mass because as mass increases, the acceleration will decrease if you exert the same amount of force. And if you decrease the mass, acceleration increases when you exert the same amount of force. Finally, we have Newton's third law, which I mentioned before, is that each action or force has an opposite reactionary force. So if forward and backward forces are the same, the net force is the same. So if we're missing any non-conservative forces, then the object will continue at the same velocity, regardless of where it started. So let's say you're running on a flat surface. If you took away the aspect of wind resistance pushing you back and you having to continue pushing yourself forward, and let's just say you weren't, actually there should be a better explanation. I don't want to spoil the problem I have later, but actually, okay, let's think about free fall. I hope, well, I guess I can explain it now, but terminal velocity is the maximum speed at which an object moves when it's falling straight down. And that's determined by the amount of air resistance it faces. What happens is gravity continues to pull the object down by accelerating it faster and faster, but at the same time, the faster you go, the greater your air resistance becomes. And so as both forces grow, there comes a point where they're exactly equal and the object can't speed up, nor can it slow down because the force of gravity pulling it down is exactly equal to the force of air resistance pushing it back up. So in that case, even if it's not stationary, the forward and backwards, or in this case, upwards and downwards force is the same and continues moving. Does that make sense? I can try to explain it at the end. But yeah, this also has to do with Newton's third law, which tells you if you hit let's say you punch something, and when you punch something, you're gonna feel it in your hands, right? Like you're gonna feel your fist impact, and you're gonna feel something push back. And that's like an example of Newton's third law, which tells you that for each force you exert on something else, that object exerts a force, the exact same force back on you. And the reason it's different is because of the masses of each object. Because if you hit like a wall, you're not going to do much to the wall because the wall's mass is so much larger than our own. And so it'll push back with an acceleration that is, you'll hit it with an acceleration that is next to nothing compared to the wall's mass. And the wall, because of the same amount of force, will hit back with a smaller amount of acceleration. And you'll see that in a later problem. And in this case, or in the case of Newton's third law, there isn't any physical contact that you actually need to experience it, because gravity is a really good example of this law. As I was talking about earlier, both humans and the Earth exert a gravitational pull on each other, but because the Earth has so much more mass, the acceleration it exerts on us to pull it towards its core is nearly infinitely stronger than the acceleration we exert on the Earth to pull it towards us. Yeah, that's actually a really great example. And I guess like if you have seen a ball bounce, when you drop a bouncy ball, it bounces back up with nearly the same amount of height as it dropped from. And the only reason it doesn't bounce back up to the same height is because of forces like air resistance. If you took air resistance away, the ball would bounce back to the same height every single time because the ground exerts the same force on the ball that the ball exerts on the ground. Thank you for that example. So now I have another set of questions for you guys, just to make sure you understand the concepts I've went over. And as always, please type the answer in the chat or unmute yourself and go ahead and say it. Great, I'm actually hearing a lot of B's. I don't know why this one doesn't have the letters, but yeah, it sounds like you guys have a really good grasp of displacement, because if you used distance, you would have gotten a non-zero answer. But with velocity, you use displacement because the woman started and ended at the same location. Her actual displacement was 0. And when you divide 0 by the time of an hour, you get 0. In this case, the average velocity would be 70 miles if instead of going back, she went further away. So let's say the airport is 35 miles north of her house. If after picking up her friend, she went another 35 miles north and that trip took an hour, her average velocity would be 70. But since her displacement was 35 miles when she got to the airport, but 0 once she came back, the average velocity is actually 0. And here is another question. And this one is a little bit of a hard one. I will admit that I got this completely wrong when I first learned physics, and that's why I thought to include it now. Well, getting a lot of A's, and I guess you guys are a lot smarter than I am because it is static friction, and that's because when tires are rolling and they have good grip, what they do is they come into contact with a specific part of the gravel or pavement or whatever material they're on, and they don't slip. So that means it's static friction. And because the force exerted by the car does not exceed the static friction, the tires are able to grip and the car is able to move forward because the road pushes back on the tires and holds it steady as the car pushes power to the wheels. If it was kinetic friction, for kinetic friction to happen, the tires would have to have worn down to the point where the force exerted by the car exceeds the static friction available, and then tires would slip and the car wouldn't be going forward properly. Hydroplaning is a great example. So is driving on ice. So what kind of friction would a ball have with a road? That depends on if it's rolling smoothly or if it's skidding along. If it's skidding along, it would have kinetic friction because the same part of the ball is coming into contact with different parts of the road. But if it's rolling smoothly, it would again be static friction because a specific point on a ball only contacts a specific part of a road until the ball rolls all the way over again, if that makes sense. Yeah, no worries. It took me a little bit to understand this. So here's one last question that has to do with Newton's third law. So for this question, I am getting a lot of B's, and that's actually the right answer. I just wanted to go through with you guys just to make sure. So when you look back at Newton's third law, what it says is a force that you exert on an object is equivalent to the force that it exerts on you at any given time. Or in other words, there's always an action-reaction pair. So if we look at the force that this man exerts when he punches the wall, it's going to be 1,500 newtons. And since there's always an action-reaction pair, we also know that the force that the wall exerts on the man is 1,500 newtons. So when you divide the force that the wall exerts by the mass of the wall, you get 10 meters per second squared. So 10 meters of acceleration, which is the answer. Yeah, thank you. Follow-up question for number 5. Well, when I said until the ball rolls over again, I just mean that it's like rolling smoothly and it's not skidding at any given point. Yes, please type the question in the chat or send it to me, Brian. But I will go back to number 5 for the second. A man weighing 50 kilograms should be different from the weight punching weight. Oh, you mean like the mass of his arm or the punch, where the punch is thrown, like his fist? In that case, yes, but I just wanted to make it simple.
I see. Thank you.
I'm not 100% sure what you mean, Brian, if I'm being honest.
Like if I am 50 kilogram weight, and if I throw a punch, the weight of the punch should be the
Because the man's mass, I shouldn't have put weight. The man's mass is 50 kilograms, and the force that he exerts is 1,500 newtons. So the acceleration he provides when he punches the wall is about 30 meters per second squared. But we don't need the acceleration because I'm looking for the acceleration of the wall.
Okay. I was wondering if a man weighs 50 kilogram, and the mass of his punch should be different.
And yes, HK is right. I am giving the force of the man when he punches the wall, which is also the force of the wall on the man, because there's always an equivalent force when you have an action-reaction pair. But going back to number 5, I was asked what I mean when I said until the ball rolls over again. Let me try to draw that. Again, I apologize for my non-existent drawing skills, but let's say this is the ball. And what I mean is if the road is like this, if the ball isn't skidding and it's rolling smoothly, this point right here, is the only place that this point on the ball touches the road. Until it rolls all the way over further down the road and this point comes into contact with the road again, it doesn't touch anywhere else except for this point on the road. Because if the ball is skidding, the same point on the ball will be touching multiple points on the road. But if the ball rolls smoothly, any one point on the ball will only touch any one point on the road until it does a full revolution on the road. I hope that makes sense. All right, sounds good. But yeah, if we're done with this question, then we can move on to types of motion. So first we have linear motion. And that all that signifies is movement in a straight line. That's definitely the most straightforward of all types of movement that I'm gonna go over. And there are a lot of equations, but what you will notice is that each equation is missing a specific variable. Like for the first one, it's missing displacement, which is delta x. So in reality, you'll only have to end up using one or two of the equations at any given time. Personally, I can say that I don't have a trick, but if anyone does, please feel free to type it. In the meantime, I will go on. A great example of linear motion is falling. So the acceleration of gravity is 9.8 meters per second squared. On the MCAT, they'll generally round that to 10 to make it easier for calculation. And what you have to understand about the acceleration of gravity is in an ideal world, there wouldn't be anything opposing it. But since we aren't living in an ideal world, we have resistance and as a result, terminal velocity. So if you've ever stuck your hand out the window when you're in a car, you'll feel the air pushing back on you. And that's a result of you displacing the air as the car moves forward. So that resistance also comes into play when you're falling in free fall as due to gravity, which is why skydivers have the ability to manipulate the speed at which they're falling by changing the shape of their body in the air. How that relates to terminal velocity is the amount of resistance you face can determine the maximum velocity you can go in linear motion. So if you tilt your hand when you stick your hand out the car door and it turns into a wing, you'll notice that it glides through the air a lot smoother and you face a lot less resistance. In the same way, when if you expand your body and act like a parachute or like spread your limbs as much as you can, if you're skydiving, you get greater resistance and that slows you down. And at a certain point, the amount of resistance that you face will be equivalent to the force of gravity pulling you down. So it'll be the same as 9.8 meters per second squared. And you won't go faster and you won't slow down because even though the forces are acting in opposite direction, they have the exact same magnitude. So there's no net force, which is the same as Newton's first law. And that if you don't have a net force, your state of motion doesn't change. And now we have projectile motion. So it's very similar, but in this case, we have movement in two directions. And we also have the components, which need to be calculated individually in this case. For the purposes of the MCAT, they're generally going to tell you that there is no air resistance. So any object that is launched will have a constant X component, while the Y component is affected by gravity. Yes, oh, sorry, go ahead and elaborate so that we can get that cleared up before we move on. Yeah, no problem.
Hello? Sorry, I was typing, but I think it's easier if I just speak. Is that okay, Nicole? Hello?
I guess as Oh, okay. I guess as they're typing it out, I can finish up projectile motion because the equations that are used in linear motion are also very important in projectile motion. Oh, sorry, I actually can't hear them. I wonder why.
I think everyone else can hear me, but it's just Nikhil. Okay, I think
Oh, I'm so
everyone
sorry.
else can hear me. Okay, so basically the trick that I learned is that, okay, so everyone else can hear me. Nikhil is the only one who can't.
I got it. I got it. I had to fix my
Okay, cool.
headphones. I'm sorry.
Okay, perfect. So Nikhil, would you mind going back to the previous slide, if that's okay, real quickly?
Yeah, not a problem. I also apologize if I ignored anyone else's question.
Yeah, someone previously asked a question, and I don't think
I'm
you
sorry.
heard.
Uh,
So basically, the trick that I learned was that with these equations, just line up your which variables they give you and which variable is missing, like you're being asked for. And all of these equations, the easiest way to remember them is they all can fall under the acronym, like the letters VAT, VAX, and TAX. So the first one is I I just refer to it as VAT, right? So it's delta V and AT. So if you're given the variables, um, say time is missing and you're given V and A, you're going to use the VAT formula, which is the first equation here. For tax, you look for the formula that's missing time. So formula 1, 2, 3, 4. The fourth one that starts with V square equals V square initial plus 2A delta X. So for that one, you're missing time. So you could use that equation to solve any question that is asking you about time. So that one is the VAX formula because it has the variables V, A, and X. So the tax formula, that one would include the variable T, A, and X, and it should be missing the variable V. So I don't know if it's here. I don't think that formula is here, but you could use that to figure out velocity. Tax. Yeah. So that's the trick that I used. If you just categorize the equations, you should be able to figure that out. Yeah, that's it. Thank you.
Also, Eric, if you're the person that asked the question, I really apologize. Go ahead and ask it now if you still haven't had it answered by me. Oh, okay. But whoever did ask the question, feel free to unmute yourself now because I can actually hear, or just type it in chat. But I apologize again. So yeah, projectile motion does have to do with the exact same equations as linear motion, and that's because we have to calculate the components of this motion independently because there are different forces affecting each component. For the X component, we don't normally include resistance because that just makes the calculation much harder. But the Y component is affected by gravity, so we do have to take that into account when calculating them. I do have a question about this later on, but I did include the equations, so it would be easier. Another type of motion in kinematics is circular motion, and I'm just going to go through uniform because it is likely the only form that they'll ask you on. I doubt uniform circular motion will ever be on the MCAT. But straight off the bat, you notice that there is no displacement because at every time that there is one full revolution completed, there is the start and end points are the exact same. Now, if you do look at the instantaneous velocity, it's going to be tangent to the circle. But since there's always centripetal acceleration, it will keep the object on the circular path. Now, this acceleration can be provided from things like tension, like a string connecting an object to a center, it can be gravity, which is why we have orbits of our planets around the sun, or it can even be due to electricity based on electric fields. I did list a couple of the equations. These two are the really important ones. There are other ones, but as far as I know, these are the only ones that really matter if they do ask a question about this. And it does help with electricity as well when you have to calculate the movement of electrons in an electric field. Finally, we have inclined planes, which really help if you're trying to learn free body diagrams, if I'm being honest. Inclined plane like this really helps you understand how to draw your free body diagrams. And thankfully, it's also only movement in 2 directions, and you do have to calculate the component forces individually. While you can't use the equations that you have for projectile motion and linear motion, it's pretty straightforward in that the forces involved are really just any exerted force, a frictional force, and gravity or the normal force. And when you draw it out, you'll notice that there's only a specific way that the gravity affects the object, in that you have a component of it affecting the normal force and a component of it working against any frictional force. Which is why if you place an object on an inclined plane and its frictional force is very small, it will start to slide down because of the component of gravity and its associated force being stronger than the frictional static force. And like I said before, an inclined plane is like a great example of getting used to drawing free body diagrams. I'm not gonna draw one, but I will work you through the process. It's just that for free body diagrams, you wanna make sure you really understand the question and how the object is located and what forces are acting on it. And like I mentioned before, for inclined planes, the forces are just gravity and the normal force plus a frictional force. And from here, you will need to use trig, but if you're not using a calculator, which on the MCAT, you can't. I actually took the MCAT a while ago. I don't remember anymore. But all you'll need is the cosine and sine functions. But they'll give you the equivalent value of putting it into the calculator. So if they do tell you a weird angle that isn't like 45 degrees or 30 or 60 degrees, they will tell you what the sine and the cosine of those angles are. Yeah, I remember now. But yeah, they do make it really easy in that they give you the exact value. So you'll realize that, oh, I might need to use sine or cosine because they'll say sine of this angle is equivalent to this value. So once you have your object and the forces drawn out, and you can calculate the normal force by using the weight of the object from mass times gravity, and then splitting it into its components. That gives you the force that creates the normal force and the force that works against the frictional force. And then you can convert that to the total force exerted on the object if you add an additional exerted force. If that doesn't make sense, please let me know. Common angles that you learn, well, at least I learned when I took pre-calculus, were 30, 60 degrees, and so on all the way around the unit circle. So it'd be like 30, 45, 60, 90, 105. But sine of, actually, maybe I can draw the circle as bad as it'll be. For the MCAT, has anyone ever used special triangles? thought of using special triangles actually in questions for this, but if the MCAT does, the MCAT can use special triangles, which makes it a lot easier. But for, MCAT purposes, the real ones you should really know, and honestly any purpose, is just 30 and 60 all the way around. So if I drew a circle, oh my God, I can't draw, but you start at 0 degrees here, where cosine is 1 and, cosine is 1 and sine is 0. There's a 30-degree line here where cosine is the square root of 3 over 2, and sine is 1/2. I'm just going to draw the sine functions because they're basically the flip of cosine. At 45 degrees, you get both cosine and sine equal square root of 2 over 2. At 60 degrees, you get cosine equals 1/2 and sine equals square root of 3 over 2, which I don't want to draw because it'll look like a random line. But yeah, if you need me to repeat that, I can as we go throughout the rest of this presentation. But those 3 angles are really the ones you need to know at any given point, especially for the MCAT. Before we get to the next set of questions, I do want to go through equilibrium. So what translational equilibrium is basically telling you that there is like no movement, no net movement of the object. And that happens when the forces exerted on the object are equal, which has to do with Newton's first law. And it's also the first condition of equilibrium. What it indicates is that, as I mentioned earlier with free fall, or just Newton's first law, is that there is a constant velocity for the object, which can either be 0 or any non-zero value. And a constant velocity means that it's going at a constant speed, which again can be 0 or any non-zero value, and it has a constant direction. So to be in equilibrium, an object doesn't necessarily have to be still. It can be moving. It just has to be moving at a constant velocity. On the other hand, we have rotational equilibrium, which occurs when we have torque. What torque is it's a type of force, or it's force exerted on an axis to rotate around a fulcrum, which is the pivot point. Torque is like an analog for force, but in rotation instead of translation. And counterclockwise rotation is positive torque, which means clockwise rotation is negative torque. And a really important point to know about torque is the lever arm. And the greater the lever arm, or the distance from the fulcrum to where the force is applied, the greater the torque, which is why when you use a screwdriver or a wrench, it's a lot easier to twist something when the handle is longer, and it's a lot harder to twist it when the handle is shorter. Like imagine hand tightening a screw. It's really hard because the lever arm is really short. It's about the length of your fingers. But when you use a screwdriver, the lever arm is long, so you can apply a greater torque to it. So rotational equilibrium occurs when, just like force, the net torque is 0. So you can have torque, it just has to be canceled out. And what rotational equilibrium means is, again, it can be moving, it just has to be at a constant angular velocity. So here we have the second to last set of questions. Again, let me know if you have a question, and type the answer in chat or unmute yourself if you have the answer. Sorry for not being able to hear you guys earlier. I will say a good place to start is the equation in the middle, because you do have most of you have your displacement. Sorry, not the equation. Yeah, the equation in the middle is a great place to start because you have everything but the time, and you can solve for that given you know what your delta x or displacement should be because you know the distance from the original height to the ground. And please type in chat if you'd like to go through this one together. Okay, we can go through this one together. If people are, yeah, okay, sounds good. So we have a couple of variables that we know already. So we know the initial height is 10, and we're looking for how long it takes the object to hit the ground. And since delta x is displacement, we know delta x should be -10 because it goes from a height of 10 to a height of 0 when it hits the ground. We also know that the initial velocity is 10. However, we're looking at vertical, like the y component of velocity, since we're only looking for how long it takes to hit the ground, not how far it goes horizontally. So in this case, we need to find the y component of velocity first. And as I mentioned before, to find the vertical component, we use trig, and it's a special angle for trig where it's the sine of 30 because we are looking at the y component, which uses sine. Yes, I can. I will warn you again, it's not going to be great, but I can definitely draw. So, or try to draw, that's probably a better way to put it. So let's say this is the ground, and let's put the person here. And this distance is 10 meters. If there was an object launched from here, and it's going to look like this at an angle of 30 degrees. Sorry, I didn't want to draw a 30 because it's going to look super bad. But at an angle of 30 degrees, what we want is this component right here. This vertical component of the launch. So to get that, the object does start where the man stands. I just didn't draw the man because it'd be a really bad stick figure because I can't draw with a mouse. I'll do it anyway because it might help. So let's say the object, which can be blue, I guess. He tosses up, and we're looking for the vertical component of this force. And the vertical component as this force is 10 sine 30, because sine gives you the vertical component while cosine gives you the horizontal component. And since the total initial velocity is 10, we need to find what part of that 10 meters per second is dedicated to vertical velocity. So when you do 10 sine 30, since sine of 30 is a half, you know that 5 meters per second is the velocity vertically in the beginning. So now we know delta x is negative 10 meters, and we know v naught, or the initial velocity, is 5 meters. Actually, delta y, but we know v naught is 5 meters. And we know the acceleration is 10 meters per second squared, but since it's gravity, it's pulling down, so it'd be negative 10 meters per second squared. Yeah, that's also true. We don't, yeah, I drew it, but yeah, you're right. If I did draw it 100% accurately, it would be at the floor level. But let's just assume that he launched it from a starting point of 10 meters, like not just the person is at 10 meters, but he launched it from a starting point of 10 meters. So when we have delta x, v naught, and acceleration, we can plug those in. So what you're going to get is something that looks like negative 10 equals 5 times t plus 1/2 negative 10 times t squared. Can everyone see that? Just to make sure that you can see me typing it out. Yes, okay, great. So when you do solve for this, it's actually gonna be a quadratic, but in this case, you could make it a lot easier by just plugging in the numbers. And what the answer would be is 2. You know it can't be 1, because if you plugged in 1, you'd get 5 minus 5. So you'd get negative 10 equals 0 in the case of 1. But if you plugged in 2, you'd get 10 minus 20, because you do 2 squared. So you get 4 here, and this whole thing would simplify to negative 20. So it'd be 10 plus negative 20. Yes, it would go higher than 10 meters when it's initially launched, but what we're looking at is displacement and not distance. Because the start point here, which I guess I'll mark in blue, for the drawing, but is the start point is here at the higher blue dot, and the endpoint is here at the lower blue dot. And since the distance is, or the displacement is 10 from the start point to the endpoint, delta x will also be 10. Does that make sense? I assume that's the question you're asking. Yeah, displacement is delta x. Yeah, with kinematics, you have to be really careful about using displacement and not distance. Oh, how I got the -20. Yes, I can do that if it'll let me edit the past box. Or actually, I can just leave it up here. So with the equation, when you plug in for delta x, which is -10, you get -10 equals v naught, which we have calculated is 5 times t plus 1/2. Oh yes, gravity is negative because it's of direction. Since gravity is working in the negative y direction, a is actually -10. And on the MCAT, it won't tell you g is -10. That is something you have to understand. So I left it like that because it's more representative. But yeah. Does anyone need a further explanation of this question? I do understand that this one was a bit more of a plug and chug because there's no direct way to calculate a quadratic unless you work it out by hand. But can we also assume gravity down is positive? Yeah, in the case of gravity, downward it is positive and upward is negative, but I would say don't treat gravity as the normal case and treat anything that says up is negative, up is positive as a special case. Treat gravity as a special case because, yeah, it is arbitrary relative to the location we choose. G isn't positive when we're considering things falling to Earth. Yeah, as long as you keep it consistent, it should be fine. But I would say most of that you're going to use gravity for, unless they're considering, as I mentioned earlier, like two masses attracting each other. Just leave gravity as being -10. Or yeah, consistency is probably best, but I would suggest leaving it as a negative. If no one else has a question about this problem, I'll wait, I guess. I can move on to the next one. Yes, the answer is C. If you plug it into the equation, it will calculate out because -10 on the left side. Yep, sounds good. This one is a little bit of practice with free body diagrams because a lot of people that study for the MCAT say that they really need a little more help with free body diagrams. And inclined planes are a really, really good place to start. And to help you guys out, I will say that the part of the gravity that you need to use or the equation is mg cosine theta to calculate the normal force. Also, I guess I can say cosine of 60 is 1/2. Great. I see you guys are getting A's, and yes, that is the right answer. Please let me know if you'd like to go through this one together as well. Okay, we can do that. In this case, it has to do with the angle that we're looking at. Generally, sine is the vertical component and cosine the horizontal component. But since we're looking at a force that doesn't, that is at an angle because of the plane, we have to look at the opposite and adjacent. Let me scroll back up to this slide. So how sine and cosine works is when you have an angle, sine gives you the length of the opposite side. So if I looked at the sine of this angle, it would give me the ratio of this side over here on the right to the hypotenuse. Cosine would give me the side adjacent to the angle, which is the bottom one. Yeah. If you like created triangles and use properties to figure it out, what you'll find is the cosine of theta gives you the normal force component, and the sine of theta gives you the force that acts against the frictional force. So for question 8, what I've told you guys is the object has a mass of 5 kilograms. And we need to find the normal force. So to find the normal force, we need to first find the force of gravity, which we can do using the mass of the object as 5 kilograms times the gravity of 10 meters per second squared. So when we do that, we get a force of 50 newtons. So from here to calculate the normal force, because Newton's third law says that each force is an action-reaction pair, we know that the normal force is equivalent to mg cosine theta. Mg sine theta doesn't give you the force of friction. It just gives you the force of gravity that works against friction. They're not the exact same in this case because friction is a non-conservative force. Yeah, so since we know the normal force is equal to mg cosine theta, we can just plug in and do 50 calculated from the mass of 5 and gravity of 10 cosine theta, and cosine is cosine of 60 is 1/2. So 50 times 1/2 is 25 newtons. And since we know that this force, mg cosine theta, is 25 newtons, and we know that both forces are an action-reaction pair, we know that the normal force is also 25 newtons. So that happens by, you have to use properties of triangles, which honestly, like, unless you know it innately, it's a matter of memorization. But yeah, mg sine is down the incline. That's actually a really good way to remember it. Thank you. But yeah, using the angle, you'll find that the angle is equivalent to this angle here, theta, to mg sine. And so you can use cosine and sine there, but that's using triangle properties. You guys are really good at coming up ways to remember these things. But yeah, if anyone needs question 8 explained further, I'm happy to do so. But if not, we can also move on to the last question, which, if I remember, is easier. I guess not. So we can move on to the last question. Okay, so we can go through this one as well. So when I said the car had the gas pedal floored, what I meant was the engine is exerting as much force as possible in the like acceleration in the positive direction. But if the car is enabled to continue accelerating, it means that the net force is zero, because when acceleration is zero, net force is zero. And we know that if we don't have a net force, the object is in translational equilibrium. This has to do with linear motion and free fall that I mentioned earlier, where the force exerted is equivalent to the resistance force. And that's why cars have a top speed, because at a point, they reach the speed where resistance is equivalent to the max amount of force that the engine can provide. I hope that clears it up for everyone. If not, please let me know. All right, guess we can move on then. So the last section I have for you is, translational equilibrium means that the net force is zero, and that does mean no acceleration, because mass is an inherent property of the object, so that doesn't change. Acceleration is what really manipulates force, and the two work together. So if there is no acceleration, there is no force, and if there is no force, if there is no net force, there is no acceleration. So the last section I have is kinetic and well, honestly, it depends based on questions and everything. I hope to be done by now, but I'll finish up in like 10 minutes at most, because this next section is very short. So the last section has to do with work and kinetic energy and potential energy. So both kinetic and potential energy are, yes, there will be a recording if you guys are in a hurry. It will be uploaded to the MCAT 101 support YouTube. No problem. Thank you so much. But kinetic energy, just like potential energy, is measured in joules. And the equation for kinetic energy, as you can see, is mv squared over 2, or 1/2 mv squared. What that means is the kinetic energy of an object really depends on how fast it's going. But in this case, it uses speed instead of velocity, because you can't have a negative kinetic energy. And kinetic energy has a special property in that it can also be measured in fluids as dynamic pressure. And kinetic energy is just the energy of motion. So potential energy is also measured in joules, but it's related to the environment that an object is in. And what I mean by that is there's gravitational potential energy. And you can see that as when you drop a pencil, it doesn't just get the energy from falling out of nowhere. That's the potential energy that you've stored in it by lifting it up to a level above the ground. And with elastic energy, that potential comes from someone or something squeezing a spring to the point where when it's released, it turns all that charged potential energy into kinetic energy. And mgh is the equation for gravitational energy. And that basically is, it's very similar to the force equation, except you also add height, because that's the distance, because work is equal to force times distance, and work is also a measure of the transfer of energy, or the method. You'll notice that elastic potential energy is also very similar to the kinetic energy equation. And that's because with elastic collisions, it's transferred basically directly from potential energy to kinetic energy. And K in this case is the spring constant, or like how much of the energy a spring is able to store. So now we come to mechanical energy, which is just the sum of all the potential and kinetic energies. And the equation for that is the total mechanical energy equals the total kinetic energy and the total potential energy. And this has to do with thermodynamics, where we know that energy can't be created or destroyed, just converted. And that's why we're able to say that the total energy is always equivalent to the potential and kinetic energies. Conservative forces. So conservative forces are forces that will not change the amount of energy available in a system. They will just convert it to different forms. And that's seen in the equation which says that the delta change in the energies is always 0. And that means that it doesn't matter what path you take, the energy will only change forms but not dissipate. And you can test if a force is conservative by using the force along 2 different paths, or measuring it after a round trip and making sure you haven't lost any. An example would be gravitational, because if you lift it back up, you have that potential energy again. A non-conservative force is a force that takes energy out of the system where it can't be used again. And that would be like friction or drag or air resistance, because those forces aren't available to the system anymore once that force is acted. So work is a method of energy transfer, and it's also measured in joules. And what work is just a measure of the force you've exerted and the distance that you've exerted it over. And the other form of energy transfer is heat. And as you can see by the equation, work is a dot product, which means that only forces that are at least somewhat parallel to the direction that the object is being displaced actually perform work. So like, let's say this, as you can see, this block is moving to the right. If you push straight down on the block, you're not doing work to the block. But if you push it from the left to the right, you are exerting work on that block. And if you push it from the right to the left, you are exerting work. Even at a diagonal, you're exerting work, but not when you push it straight down, because there's no component of the force that you're pushing down that's helping the block move to the right or the left, which is its displacement vector. And then we have pressure, volume, and work. So these are pressure volume graphs, which can be related and combined with work when you're looking at like cylinders and pistons in an engine. What you want to know about these is you can calculate the amount of work done based on the area that the curve follows. So like in the graph given, you can calculate the amount of work done by calculating the area in the gray. So what happens here is when you compress a gas, you're displacing the gas into a smaller area. And so you're performing work on the gas. In the opposite way, when the gas expands, it is performing work by displacing air or whatever else it is pushing to take up more space. Isovolumetric processes, or isochoric, just means that as you can see from 1 to 2, the volume doesn't change, so there's no actual work done. But on the other hand, where the pressure stays constant, it's called an isobaric process, but work still is done because there is still volume being displaced, even if the pressure is constant. So the measure of power is just the rate at which work is performed, and it's measured in watts or joules per second. And so the equation for power is just work over time, or the change in energy, which is an equivalent for work over time. And this is also why we have horsepower, because a long time ago, that's what someone used to measure how well their engines could work, by comparing it to the work that horses could perform. So we have the work energy theorem, which relates work to kinetic energy. Basically, all it says is that the work done on an object influences the kinetic energy. The work is responsible for the change in the object's kinetic energy. This theorem also allows us to calculate work without needing like force or displacement. We can just use kinetic energy change to calculate how much work was done. And this is similar to the first law of thermodynamics. Finally, we have machines, which are just devices that people use to give us an advantage in how much work we perform. And you can see that in the calculation of mechanical advantage, which is the ratio of a force that we put in on one of these machines to the ratio of the force that the machine puts out on the object. And examples of simple machines are like inclined planes, which you'll see later as instead of moving something straight up and using a great amount of force to move it a small displacement, we can increase the displacement and lower the amount of force needed, which is why you can push, it's always easier to push something up a ramp instead of carry it straight up. And also why we have cars, because wheels, and we have wedges and levers having to do with torque, and we have pulleys, which I'll get to later. And basically what a machine does is it reduces the amount of force that we need to exert, but to get that advantage, we need to increase the amount of displacement. And finally, we have pulleys, which are one of the simple machines. And what you need to know about pulleys is the load, which is the weight that the pulley is carrying or lifting, the effort, which is the amount of force that we exert on the rope to lift the load distance, which is the distance that we actually lift the load, and the effort distance, which is the distance that we actually pull on the rope connected to the pulley. Ideally, pulleys are massless and frictionless, but again, we don't live in an ideal utopia. So ropes do have mass, so they add to that load. We need to lift more because of ropes and the pulleys. And they also have friction, which means that's another force that we need to include when we consider how much the load is. And that has to do with efficiency, which is how well the energy we're putting in is conserved and transmitted to lifting the load. What we notice is that adding more pulleys, while if you look at the graph, adding a pulley increases or decreases the amount of force needed to lift a load, but it also increases the effort distance by the same amount. So we'd expect that adding like a lot of pulleys would make the force super small, and so we could easily pull it a longer distance. However, adding more pulleys actually decreases our efficiency, so we will get diminishing returns because the pulleys have mass and friction, which increasingly add to the load that we actually have to lift. And you'll notice you can calculate how efficient pulleys are by putting how much the load is actually being moved or changed over how much effort we actually put in. And ideally, the efficiency is 100%, but since we have mass and friction in pulleys, we decrease that. It doesn't go that high. But yeah, these are the last set of questions for you guys, and then I'm willing to answer any other questions that you guys may have. I also apologize if you can hear my computer fans. For this question, you'll just need to relate the gravitational potential energy to kinetic energy. And let me know if you need the equations for that. Yeah, so the equations have to do with potential energy, which I will scroll up back to real quick. So this is an equation you'll need. You'll need the kinetic energy equals 1/2 mass times velocity squared. If you want to write that down or put it to your notes. And you'll also need potential energy equals mgh. And the reason that this works is actually because of this law of thermodynamics and the conservation of energy, saying that we can directly translate mechanical energy to, potential energy to kinetic energy. And if there is a difference, that means there's non-conservative forces at play. I'll give you guys about another minute and then. Okay, I'm gonna go ahead and, because I don't want to keep you guys for too long. Yeah, this is great. Yeah, he does lose a lot of energy to non-conservative forces, which is pretty realistic considering like the faster you run, the more you feel the wind pushing back and the more energy you lose. But if we're good with that one, I can move to question 11. But this one just has to do with setting mgh equals 1/2 mv squared and then solving. For this one, it's just basically memorizing the most important, or at least calling back the most important equations having to do with kinematics. You need the equation for force, for work, and for power. Were the numbers for question 10? I actually don't remember off the top of my head. I will calculate it right now while you guys answer this question and get back to you. For question number 10, the answer, I did get 12,500 for the potential energy, but I do believe I got 100 for kinetic energy. And that's because it's, think I calculated right, it's 1/2 mv squared, because m is 50 and v is 2, so. Yeah, great. Okay, we can go through it if you're not sure how to use the equations. This one is just like a combination of the majority of the main equations for kinematics. If you're all good with that, I'm going to go ahead and go through it because I don't want to keep you guys here for too long. So for this question, you're going to need F equals ma. So we can start with calculating the force that the bodybuilder exerts. So that's 20 kilograms times 0.25. So that gives you a force of 5 newtons. And then we use the distance of 1/2 meter to get work. So force as 5 newtons times distance as 5 newtons times 1/2 meter. You should get 2.5 joules. And since power, oh, I guess I didn't ask directly for power, but yeah, since power is work over time, and we have 2.5 joules as work over 2 seconds of time, the answer should be 1.25 watts. Does that make sense? Great. If no one has a question about this one, I will go ahead to the last question that I have for you guys, or anything. What you really need to remember for this one, which has to do with pulleys, is that the number of pulleys and the force needed and the effort distance are directly proportional. They're actually inversely proportional. So if you decrease force, you increase effort distance. And if you need me to explain effort distance, load distance, and effort, I can do that again. Great, I am getting C's, which are the right answer, or which is, I guess. If you want me to go through it, yes, I can go through the equation for this one. This one is more, it's more of like, it's not a direct equation that you'll see. It's just, I guess it's better to draw it out. I can definitely draw it out in this case. This one's pretty straightforward to draw out. So we have, let's say, 2 loads, and each one is 100 newtons, right? Then we have 2, in the case of the original pulley, we have 1 pulley that bears 100 newtons. And in the case of the second example, we have 4 pulleys that each bear 25 newtons. Yeah, it's not a specific formula. It's just that if I go back, I'll actually show you. If I go back to this slide, you'll notice that when you add more pulleys, or the proportion of pulleys to the force is pretty, is it inversely? Yes, it's inversely related. So when you have one pulley, each pulley lifts 100 newtons. When you have two pulleys, each one lifts 50 newtons, so on and so forth. You divide the load by the number of pulleys. But like I said, when you use machines to reduce the force needed, you also increase the effort needed or the displacement needed. So when you divide the force by 2, you increase the displacement by 2. Because the work never changes. It's just you're making it easier for yourself by reducing the amount of force needed at any given time. Does that help? Okay. Yeah, no problem. With that, I am pretty much done. I do want to remind you guys, we are a nonprofit. We're all just volunteering and helping out. Please consider donating. And yeah, no problem. And thank you. If you have any questions, email me, email mcat101. And if you want to be added to the list, please put your email in the chat. And if I said I'd answer a question of yours, I apologize for taking so long to get here, but I am available right now. Thank you, guys. Yes, good night. Hope you guys had a happy new year and holidays. And if you guys are going back to school, good luck with your next semester. Yeah, I did get a question about number 8. Oh, right, okay, yeah. What would be the normal force experienced by the object? Okay, Brian, let's see here. If I go back to this slide, we can work that out, right? We know that, yeah, mg cosine the mg cosine 60. Yeah, that's, yeah, F normal is equal to mg cosine 60. So I do think you have everything right. I'm not sure what you're asking. This was number 8. The correct answer is choice A, actually. So 25 newtons. But yeah, all your work is perfect. Does anyone have any other questions?
Hi, I have one more question.
Yeah, what's up?
When we usually when I think an NCAP is a very long test, and usually when I do the content review in the end, especially like when I do the practice exam, I often forgot a lot of things that I learned previously.
I can relate to that.
And how do you usually maintain the information? Do you think it's a good idea to using the mile down Reddit review sheet and just read everything like maybe once a month or twice or 2 weeks?
I would say, yeah, definitely review is one of the best things. Review and like redoing, not redoing questions, but doing more questions of stuff that you've done in the past, but it's been a while. So like, I'm sure this is probably like, in terms of physics, this is the first thing you come across. So reviewing something like this is definitely fundamental to doing well, because it really is the basics for everything else in physics.
And when we're doing the review, how would you suggesting this like personally the best way for you to maintain it?
Gotcha. I will say it's on a case-by-case basis, but what I do is I try to do a set of questions that corresponds to like all the different sections or subsections from a part of the MCAT. So like if it's been a while and I want to review physics, I'll try to pick a couple questions that have to do with all the different concepts under physics. And I'll do them and I'll look at them and see, okay, this is what I got wrong. This is what I wasn't confident about, and really go back and read those concepts again. Because when you're in a time crunch, which you won't feel like you are when you start super early, but you'll get there, you really want to focus on the areas that you have, you really want to, I guess, remove your weaknesses. And you want to find what those weaknesses are super early. So I'd really suggest just try to get a couple questions from each concept and really find out where you're not sure of yourself.
Okay. Do you using any kind of quick sheet or any kind of review sheet that you use, or you just directly do the back to the Kaplan textbook summary or Kaplan textbook?
Yeah, personally, I don't use a quick sheet because like it feels a little bit like a cheat sheet to me, and I'd really miss it if I studied with it and then got to the test and realized I couldn't use it at all. What I do is I just make sure to note down everything that I'm having trouble remembering or having trouble applying properly, and look at that, and then just reiterate those concepts over and over through the form of questions until it really just sticks in my head.
Yes. Thank you so much.
No problem.
And thank you so much for tonight.
Oh, no, I definitely
very helpful.
Thank you for you guys being here. All right, any other questions? If not, I'm gonna go ahead and end this session. I guess I'll wait another minute, just in case. Also, this session will be recorded, or is recorded and will be posted. So thank you guys for being here.